Folks. So there are a few things that I need you to have out before we begin. I'd like you to take out the calculator commands. I asked you to print 6 different things for today, right? And I said you could forget the 6th one, but you'd at least need the first 5, right? I need you to open up the calculator helpful commands for Texas Instrument Calculator, that one. And if you could open that to the last page. Then I need you to have the typed lecture notes, comparison of means of 2 populations. We're going to begin with that. And I would like you to have the lecture notes that say page A in the right corner. I also need you to have this one that says F test. Maybe yours looks a little different. Let me see the other one. Yeah, I need you to have this one that says A on the bottom right, and then there's another set of handwritten notes. Yeah, F test to check for equality of variances. We need that out as well. Let me see what else. You don't need the chi-square lecture for today. You can put that away. You don't need this example, a patient's blood volume. You don't need that. You can put that away. You need your chi-square tables and F tables and every other table. Okay, so you need your tables out. And let us begin with the typed lecture notes. On page 14. Page 14. When comparing 2 populations, it would be ideal if the 2 populations were similar in all respects, except for the 2 treatments being imposed. The main advantage of the paired design is to reduce the effect of bias due to confounding factors. Subjects can be paired with respect to factors such as age, gender, health status, etc. The units in each pair are alike, but pairs can be dissimilar to other pairs. So in this new business that we're doing now, we are comparing means. Previously, we had done hypothesis testing regarding one mean. Mu equals 10 against versus mu not equal to 10, greater than 10, less than 10, right? That's what we studied before. Now we're trying to study to see if 2 means are the same, or if one is bigger than the other, less than the other, or not equal to the other. Okay? So the easiest design is the matched pairs design. So I want to start there. Matched pairs. And if you follow along, this is on page 14 of the lecture notes. And H naught would be mu1, this is on the bottom of page 14. Mu1 equals mu2 versus HA mu1 not equal to mu2, which would be 2-sided, or mu1 greater than mu2, which would be right-sided, or mu1 less than mu2, which would be left-sided. So now we are comparing means. You follow what's going on? It's not just mu equals 10 versus mu not equal to 10 anymore. Now we're comparing the means of two different populations. So the first thing I do is bring this guy to the left side. So this becomes mu1 minus mu2 not equal to 0, which I write as mu difference not equal to 0. And this one, when I bring to the left side, it becomes mu1 minus mu2 equal to 0, or just mu difference equals 0. You follow what I mean? So D stands for difference. So mu D equals 0 versus not equal to 0, or mu D greater than 0, or mu D less than 0. So this is the null, and one of these alternate hypotheses will hold, depending on two-sided, right-sided, or left-sided. So as we said, the subjects are matched. For example, twins, right? You give one treatment to one twin and another treatment to the other twin. The twins are alike in all respects except for the treatments that are being imposed upon them. You follow what's going on? So this is the simplest kind of comparison of means, where the subjects are matched. And the pairs are independent from one another, but the subjects within the pair are not independent because they are twins, right? So the way to do this kind of study, you already know, it's a t-test. It's just a t-test. So if you look on page 14, you have the test statistic. You're going to do a t with n minus 1 degrees of freedom, depending on whether it's two-sided, right-sided, or left-sided, just like before. So if it's two-sided, you're going to split your alpha, alpha over 2, alpha over 2. If it's right-sided, the entire alpha will go in the right tail. So here, let's label it two-sided, right-sided, left-sided, just like before. And T naught equals the mean difference, D bar. Remember we had X bar before? Now it's D bar minus mu D under the null. So let's call this mu D from the null. In my case, it's 0 here, right? Divided by S over rad n. Same formula. X bar minus mu over S over rad n, just like it used to be. There's no difference at all. And that's the formula that you see on page 14. And then, depending on where this falls, you reject or you do not reject accordingly. So this kind of stuff you already know. It's just a review. And in order to do this on your calculator, you're just going to do stat, test, t-test, right? You would put your data. If they gave you data, you would find the differences and put it into L1, and then you would choose the data option, and then you would do stat, test, t-test. So on the calculator, you would put differences into L1. So you'd go stat, edit, and then put it into L1. And then you're just going to go stat, test, t-test. And then data or stats, you're going to choose data because you have a list. You'll have a list of differences. We're going to do examples so you'll see very clearly how this works. Choose the data option, and then the list will be L1, and the frequency will be 1. And and you will put in whatever else they ask you, and it'll spit out T naught and the p-value. So I would like to begin doing the example on page 17. And this example has been done for you on the left side of page A. Right? I'm in these notes that are landscape. This is landscape, right? On the page 1. Okay? So let's read it carefully and just do it. It says, although the Occupational Safety and Health Act, OSHA, is not very popular with management because it is expensive to implement, some sources claim that it has been effective in reducing industrial accidents. The following data was collected on lost time accidents before and after OSHA. The figures given are mean man-hours lost per month over a 1-year period at 6 different industrial plants. So this is a before-after study, which makes it a matched pair study. Okay? Right before and right after. Part A, state the hypothesis to test if OSHA has been effective in reducing the average number of man-hours lost per month. Reducing. So we got to set this up properly. And if you follow here, you would have seen me set it up. So H naught, let's label this properly, page 17, the OSHA example. H naught is that mu before is equal to mu after, and HA would be that mu before is greater than mu after, because they're saying, has it reduced? It says, has OSHA been effective in reducing the average number of man-hours lost per month? So I want to see if the after is smaller than the before. In other words, before is bigger than after. Agree? Now I bring it to the left side. So this becomes mu before minus mu after equals 0 versus mu before minus mu after greater than 0. So this will be a right-sided test. And then they gave you a whole bunch of data some numbers for before and some numbers for after. So you have 38, 31. The first thing you're going to do is take the difference. And because your difference is before minus after over here, I'm going to do this minus that. So this would be 7. And then the next one would be 64, 58. Before minus after is 6. And so forth. And you see this list, it's been done on page 1 of that landscape package. 7, 6, minus 1, 5, 6, and 1. This is your list of differences. So the first thing you do is you find these differences and you immediately put this into L1. Go ahead. Put this list into L1. Stat, edit. Make sure that list is empty. If it's not, go up to the name of the list and hit clear and hit enter. Make sure that list is empty. And then stat edit and then put this into L1. Put data in L1. Once it's in L1, you're going to go stat, test, t-test. Data or stats? Data. Now, since it's my job to show you how to do this by hand, instead of doing stat, test, t-test, and data, why don't we go stat, calc, one variable statistics on L1. If you do that, it will actually give you the mean difference and the standard deviation of the difference, so I can work up the test statistic just to show you, right? So do this and tell me what your D bar is, your D bar and your S of the differences. Give me those two numbers. Can you do that? Yeah, D bar turns out to be 4. You actually did this, right? I want you to play with it so it gives you the mean and the standard deviation. So D bar equals 4 and SD equals 3.2249. Once you have that, you can go find your test statistic. T naught equals D bar minus mu D from the null divided by S over rad n. And when I put this in, I get 4 minus mu D, this is mu D, equals 0 under the null hypothesis. So this would be 0 divided by S. S is 3.225, right? Over rad n. 1, 2, 3, 4, 5, 6 values. Radical 6. Clean this up and you get 3.038. Now, if you did stat, test, t-test with data, you should get the same test statistic, right? Now, this test is right-sided, so the entire alpha will go in the right tail. I don't know if they gave me alpha. Yeah, they did. They gave it to me in part C. So part C, the alpha was 0.05. I put that here, and I go to T n minus 1 degrees of freedom. N minus 1 would be 5 degrees of freedom. This is like a review of what we've already done, right? 5 degrees of freedom. So can we please go to our 5 degrees of freedom and look up our critical value? I'm looking under the O5 column. 0 is here. What do you see? Yeah, agree. 2.015. This is the critical value. Let's go drop the test statistic to see where it falls. 3.038 falls to the right of the critical value. So here, 3.038 falls to the right. Therefore, I will reject H naught in favor of HA. Conclusion, reject H naught in favor of HA. So HA says, where's my previous slide? HA says mu before is greater than mu after. So there is a reduction. There is significant evidence of a reduction. So there was improvement. Could I do a confidence interval for this problem? The answer is no, because it's not two-sided. No confidence interval. Let's find the p-value. Well, it's a right-sided t-test. So p-value would be t-CDF, left endpoint 3.038, right endpoint infinity, and degrees of freedom 5. What do we get when we do that? I want to do it right now. So, second, VARS, TCDF, left endpoint 3.038, right endpoint 1000, degrees of freedom 5. I get 0.0144. I compare against alpha. Alpha equals 0.05. P less than alpha. Reject H naught. Agree? If I had to estimate the p-value, it wouldn't be a big deal. I would go to my 5 degrees of freedom. Let me do that right now. Let me find a t-table. So I go to my 5 degrees of freedom and I try to place 3.038 somewhere. 3.038 is the T-naught. And it lies between 2.571. Follow along with me on your T-table, guys. I'm in 5 degrees of freedom. And 3.365. And then I go up these columns. And I see 0.01 for the right one. And 0.025 for the left one. So my p-value estimate would be between 0.01 and 0.025. And this number, 0.0144, is in this interval. So it matches what my estimate would be. So this is the estimate of the p-value. Let's label that properly. Estimating p-value. So I went to T 5 degrees of freedom row. And that's that. Are you with me? The next problem that I would like you to try before you come back for the next class is the problem on page 18. It's exactly like the one I just did. Try page 18. I want to set up the null and the alternate though, because once you know what side the test is, it's very easy to do. So let's go to page 18. I'm missing my page 18. Would somebody mind reading page 18 to me? My packet is missing page 18 for some reason. Would you just read me page 18? Nice and slow and loud, okay?
An investigator believed that people who smoke tend to smoke more during periods of stress. He compared the number of cigarettes ordinarily smoked by a group of 18 randomly selected subjects with the number they smoked during the 24 hours prior to a predefined stressful event. Test the appropriate hypothesis using a significance level of 10%.
Okay, so it looks like they give me columns of values. What are those columns called?
Person's usual number number prior to stress and differences.
Okay, so H naught would be mu usual equals mu prior to stress. And I'm testing to see if the person smokes more just prior to stress, right? So it would be mu usual less than mu prior to stress, because I'm looking to see if they smoke more in stressful situations. Correct? So when I bring this over, this would be mu d equals 0 versus mu d less than 0 if my subtraction is going to be usual minus stress. So my differences are going to be usual minus stress. And I would do exactly the same thing as I did in the previous problem. So I would like you to do this problem as practice before you come back for your next class on Monday. Okay? That's the first part of your assignment. Okay. Any questions on this method? It's just a t-test, the same kind of t-test we've been doing all along. Let's go to a different method unless you have a question. Okay, so the next thing I want to talk about is in the beginning of the packet, and I'm on page 1. Of the type notes. This time I have independent samples. So you will be given, if you turn to page, I'm going to flip back and forth between the second half of page A and the first half of page B. So in this type of example, you will be given two populations, say X and Y, and you will have a sample of size N1 here and a sample of size N2 here. If you want to follow along, I'm on the second page of this packet. Okay, I'm on the second page right here on the left-hand side. I'm just reading from there. Okay, so I have a sample of size N1 from the X population and a sample of size N2 from the Y population. Then they're going to give me the sample average here, which I'm going to call X bar, and a sample average here, which is called Y bar. And they will give me SX or SY and SY. That's one kind of problem. The other kind of problem is where they give me X and Y, and they give me N1, N2, and X bar, Y bar, but they don't give me SX and SY. They give me sigma X and sigma Y. So if they give me sigma X and sigma Y, then I'm going to do a z-test. If they give me SX and SY, I'm going to do a t-test. Just as we've always done. If you know sigma, you do z. If you don't know sigma, you do t, right? So, having established that, I want to go see where the stuff is. So I'm on page B on the left-hand side still. So here it's going to look like what you see on page 1 of the typed notes. it'll look like this. H naught mu x equals mu y versus HA mu x not equal to mu y, mu x greater than mu y, or mu x less than mu y. So again, two-sided, right-sided, left-sided. And again, I bring the stuff to the left side just like I did in the last example. So this would be mu x minus mu y not equal to 0, mu x minus mu y greater than 0, and mu x minus mu y less than 0. And let's say that I'm talking about this case where sigmas are known. Sigmas are known. So I will be doing a z-test. To find the test statistic, I have to take the x bar minus the y bar that they're going to give me. You see these x bar and y bar? My job now for the test statistic is going to be to turn that into a z. Just like in the early days, wasn't I turning x bar to a z? Remember this formula? Remember this? Z equal x bar minus mu naught over sigma over radical n. Remember that? Similar to that, I'm going to now have to change the difference in the sample means to a z. Because after all, I'm testing mu x minus mu y equals 0, right? So now, I'm going to be doing z equals x bar minus y bar minus its mean divided by its standard deviation. And it's my job to figure out what is the mean of this x bar minus y bar and what is the standard deviation of this x bar minus y bar. And that is what you see on this page B on the left-hand side, is me trying to derive what the mean and the standard deviation would be. So this is of course called E, expectation, which is another word for mean. E of x bar minus y bar, and this one would be called sigma of x bar minus y bar, right? Do you see what I'm trying to show you is that whenever you're trying to change something to a z, you always have to do it minus whatever its mean is divided by its standard deviation. So I have to come up with the mean and the standard deviation. So let us find this mean and let us find this sigma. And that's what I have done here on page B. So E of x bar minus y bar is equal to E of x bar minus E of y bar. So E of x bar, I know, is just E of x. And E of y bar is E of y. We know that. Remember when we were learning the sampling distributions of the mean? We said that x bar has the same mean as x, but a different sigma. Remember that? That's the rule that I'm using. So these means are the same. So this one would just be mu1 minus mu2, or mu x minus mu y, which is equal to, I'm using 1 and 2 and x and y interchangeably. So that's equal to mu x minus mu y from the null. Whatever that is in the null, that is what will go in here. And then I also have to figure out what sigma x bar minus y bar is. So the first thing I will do is find the variance and then take the square root. So variance of x bar minus y bar is equal to variance of x bar plus -1 squared. Remember, the coefficient gets pulled out and squared. That's what I'm doing here. This is a -1 right here. Variance of y bar. Then I know that the variance of x bar, I know that sigma x bar is sigma x over rad n. I knew that from before. So the variance will be the square of that. So sigma squared x bar would be sigma x squared over n, which is what I'm using here. Sigma x squared over nx plus sigma y squared over ny. And since I want the standard deviation, I'm going to take the square root. So sigma of x bar minus y bar is equal to the square root of the variance of x bar minus y bar, which is equal to the square root of sigma x squared over nx plus sigma y squared over ny. And this term is what would go here. So this is my denominator. So when all is said and done, I get this formula for the test statistic. Let me call this Z0. So I have this formula, Z0 equals x bar minus y bar minus mu x minus mu y from the null divided by radical sigma x squared over nx plus sigma y squared over ny. I want to point out to you that this is a plus because this -1 got squared. So this is a plus, okay? Don't make the mistake of writing minus there. Are you with me? Now this is my base formula that I'm going to keep on coming back to, and I will make variations on this depending on whether my S's are given or not. Oops, I don't mean to do that. So in this situation, I'm going to have to refer back to this formula and make some changes. But this is the main formula, and I will make some changes to it depending on what the situation might be. So keep that in mind. I want to do an example using this formula right away, and that would be the SAT example, which you see on page 4B, B, the second half. So the question is, are SAT math scores for males equal to SAT math scores for females? So do guys and girls do just equally as well on the SAT is the question. So we're comparing mean SAT math scores for males and females. And they give you all the information you need. You have males. So let's call that N1 or NX, however you want to call it. 19,883 is the number in your sample, with a sample average X bar equals 416 and sigma X is given 87. And then you have another population, females, from which you take a sample of size N2 equals 19,937, Y bar equals 386, and sigma Y is given to be 74. I am just reading from page B, the second half, okay? So I want to see if SAT scores are the same or not. So H naught mu 1 minus mu 2 equals 0 versus HA mu 1 minus mu 2 not equal to 0. It will be a two-sided test, and it will be a z-test because sigmas are given. Follow? So let's create our z. Two rejection regions. I don't know if they gave me an alpha or not. No alpha given. Let's just start saying that. No alpha, therefore use 0.05 for alpha. So I'm immediately going to split my alpha into 0.025 and 0.25. I label this Z. I go to the bottom of my T table and look up the critical values, just like I always have done. And I see 1.96 and minus 1.96. Critical value, two critical values because there are two rejection regions. Then I find my test statistic, Z naught equals X bar, 416, minus Y bar, 386, minus this 0 from the null hypothesis, divided by radical sigma x squared, 87 squared, over nx, 19,883, plus, make sure it's plus, sigma y squared, over 19,937. And when I clean this up, I get 37.06. And then I go and I drop this 37.06, and of course it falls in here. 37.06, which is in my rejection region. So conclusion, reject H naught in favor of HA. HA, which says that mu1 minus mu2 is not equal to 0. Furthermore, you're in the right rejection region. Right rejection region. So conclude that mu males is greater than mu females. Because I'm concluding that mu1 minus mu2 is greater than 0. Do you see how this is everything that you already know? Just a little variation, because now we're comparing means. Get it? Okay. So all this was on page B, right? Any question on this? What if I had to find the confidence interval? Would that be appropriate for this problem? It's a two-sided test, so confidence interval would be appropriate. How would I find the confidence interval, do you think? Let's see. What was your formula before for confidence interval? This was page 4, so I'm on page 5 now. Suppose I knew nothing, right? But I knew my old confidence interval formula. Could I create a confidence interval formula in an emergency situation? Could I? I think we could. Before we had this, x bar n plus or minus z alpha over 2 sigma over rad n. Remember this formula? Now what do you think it should be? Don't look at your notes. Can you make this up? Instead of x bar, I'm going to have what? X bar minus y bar, because I'm looking for the difference in the means. So x bar minus y bar plus or minus z alpha over 2, and then not the standard deviation of x bar like you saw here, but the standard deviation of x bar minus y bar, which I just derived right here, didn't I? Wouldn't this term go here? Radical sigma x squared over nx plus sigma y squared over ny. That's it. That's how you make a confidence interval formula, right? How do I know that? Because I knew that this term is just standard error. That was the standard deviation of this guy. So this better be the standard deviation of this stuff. And it is. And I'm done. Get it? So nobody does all this by hand, really. Your whole entire final can be done on your calculator. Let's figure out how to do it on the calculator next and make sure that we get the same answers. So if you look at your calculator commands on the last page, comparison of means matched pairs was given on the last page, and we talked about this. It's just stat test t-test or stat test t-interval, right? If it's two-sided. So look at the last one, the very last one on the formulas page. That stuff you already know how to do. This stuff, comparison of means, is on the previous page. You go to stat test two samples z-test. I don't even know if I put that on here because most times we're doing a t-test. Yeah, this was a z-test because sigmas were given. So this would be stat tests two sample z-test. See if you can find that on your calculator, and let's go through it to see that we get the right answer. Stat test two sample z-test. It's number 3. Right? Please do it with me. Are you inputting data or are you inputting statistics? Statistics, because in this example they gave me x bar, y bar, and all that stuff already. They did not give me raw data. So I'm going to choose statistics and hit enter. Sigma 1 equals 87. Sigma 2 equals 74. X1 bar equals 416. Y bar, no, N1 equals 19883. X2 bar equals 386. That's my Y bar. N2 equals 19937. And the most important thing to do is to choose the side of the test. My test was two-sided, so pick the first option and hit enter and go down and hit calculate, and voila. Z0 equals 37. What did I get? 37.06, and so did they. Right? So the calculator does the whole damn thing for you. There's no reason why you should get under a 90 on the final. Agree? Okay. Keep scrolling down. Down arrow, down arrow. Will it give you the p-value? It says p equals 0. Does that make sense? P-value equals 0. Look at my p-value, guys. I am here. Here's the z. Oh, come on, pen. I am here. Here is my 1.96, and my 37.06, which is my test statistic, is way out here. And what the p-value equals 0 is saying is that the probability of being more extreme than 37.06 is 0. So p-value equals probability z greater than 37.06. So certainly makes sense that the p-value would be 0. And then of course p is less than alpha. Actually the p-value would be two-sided, right? So there's another 0 on this side. There's nothing there. So p is less than alpha, which was 0.05. So reject H naught. And it all ties in together. Are you with me? Quite easy if sigmas are given. So next, let's talk about the case where sigmas are not given. And S's will be given, okay? That's next. Any question on anything I've done so far? Okay. 1, 2, let's see. 3, 4. Okay, now assume sigmas not given, but S's are given. S1, Sx, and Sy given. So let's see where that stuff is in these notes. I'm back on page A. Refer to page A, please. And I'm looking at the second half of page A. So first of all, if Sx and Sy are given, and if n's are large is greater than 30, we used to say, if n's are large, then assume that sigma and s is one and the same and just do a z-test. Because as we know from the t-table, as you go down, as n gets larger and larger, the values are approaching the z. So your results won't be much different. That's what this top of the page 2 on page A is saying, right? It's saying if n's are large, then assume that you know the sigmas and just do the z-test. But really, what I would like to teach you now is don't even bother with that. Let's do the real t-test. Let's say that the s's are given. The first thing you have to do is decide if the variances, which are unknown, for the two populations are the same or not. That's the first thing you have to do. In other words, you have to do an F test. To decide to do this, you have to do an F test. Do an F test to first decide if the variances are the same or not. And I want to see where that was done here so that you don't have to keep writing. Page C. If you turn to page C. So this F distribution is an asymmetric distribution. Looks something like this. And it's based on two items: the numerator degrees of freedom, comma, the denominator degrees of freedom. And 0 is here for F distribution. Minimum value is 0. The 0 lies here for the F distribution. And I'm going to be testing this. H naught, this is on the bottom of the left half of page C. I'm right here. So I'm testing H naught, sigma 1 squared equals sigma 2 squared versus HA, sigma 1 squared not equal to sigma 2 squared. Because after all, the first thing I have to decide is, do these two populations that I'm talking about here, whose S's are given to me, do they have the same variance or do they not have the same variance? So I'm going to use the S's to decide if the variances are the same or not. So the next thing you do is create two rejection regions, because this is a two-sided test, and split your alpha. So let's say that alpha equals 0.02. I'm copying from page C, left-hand side. So I'm going to split this alpha, 0.01 here and 0.01 here. And this, since this is not a symmetric distribution, the two areas are the same, but they look differently in the picture, right? But they're still 0.01 and 0.01. Now, very important to notice that this is the only one you care about. I only care about the right critical value. And the reason for that is because my test statistic F naught, and I'm still reading here from page C on the left side, F naught, the test statistic, is created by taking the larger S squared over the smaller S squared. So you see, this test statistic F naught will always be a number greater than or equal to 1. F naught will always be greater than or equal to 1 because you have always taken the larger one and put it in the numerator. So because this is a 0 value on the left hand and the minimum value is 0 for F, I only care to see if this ratio exceeds the right critical value. I don't care about the left one because this is going to be some really small number, and I don't care about that because my F naught is always going to be greater than or equal to 1. So I want to see, is it greater than this critical value or not? Follow? So two things can happen here. Based on this, two things can happen. Either my test statistic F naught falls here, or the other scenario would be that my test statistic F naught falls here. And remember that H naught is equal to sigma 1 square equals sigma 2 square versus HA sigma 1 square not equal to sigma 2 square. Before I begin any comparison of means, I have to decide whether they came from the same populations with the same standard deviation or not. That's what I'm trying to do here. So if it falls in here, to the left of this critical value, which is the only value I care about for the 0.01, then I'm going to say that do not reject H naught and conclude that sigma 1 square equals sigma 2 square, and carry out a pooled variance t-test when the F test is not significant. So clearly my F test was not significant. I was not in the rejection region. And that's telling me conclude that sigma 1 squared is equal to sigma 2 squared because I don't have enough evidence that they're different, right? So I'm going to carry out a pooled variance t-test in this scenario. And in the other scenario, I would be in the rejection region, so reject H naught in favor of HA, and HA says that sigma 1 square is not equal to sigma 2 square. And then carry out a Welsh-Satterthwaite approximation. So this is an unpooled t-test. So you don't have to memorize all this, you just have to understand it. If your F test statistic falls in the do not reject region, which it did on the left side, then you're saying don't reject the fact that the sigmas are the same. So if the sigmas are the same, we're going to pool the data together and carry on a pooled variance t-test, because we're saying let's pool the variances if the variances are the same. Here we're saying the variances are not the same, so we're not going to pool them. We're going to do an unpooled t-test. Are you with me? That's the first thing I'm going to do. And then this t-test, this pooled variance t-test, by the way, is performed at nx plus ny minus 2 degrees of freedom. This pooled variance t-test. I'm just giving you a summary of where we're going. And here, this unpooled t-test would be carried on at nu degrees of freedom, where nu has a complicated formula and you should rely on your calculator to find nu, because if you screw up on the nu formula, then you're going to screw up on your critical value too. Rely on calculator, but round down. And you'll see what I mean when we do that. This is nu. Mu looks like a U. Nu looks like a V. Peter, you had a question. The pooled variance t-test would be performed at nx plus ny minus 2 degrees of freedom. It's a much more complicated, I mean, the test statistic is more complicated, but I'm saying the degrees of freedom would be nx plus ny minus 2. Here, the degrees of freedom would be nu, which has a complicated formula, which I will bring you to when we discuss that. Are you with me? It's all about the F test. The first thing you do is the F test if they give you S's. So I had said over here, the numerator degrees of freedom, comma, the denominator degrees of freedom. So you decide the numerator degrees of freedom based on which of the populations has the larger S. You cannot do this on the calculator, okay? I want to make a note of this. The F test must be done by hand. Must be done by hand, because the calculator does not take the larger one and put it on the top. And it's going to give you the wrong F test statistic if you rely on the calculator, okay? So this one must be done by hand. And then this numerator degrees of freedom will be the n minus 1 that goes with the population that had the larger variance. Let me write that. So the numerator, it's just a lot of words.